In Chem 1, we learned about acids and bases in this chapter where we learned about solutions. And one of the things that we learned is that acids are substances which produce the hydronium ion in water. This is known as the Arrhenius definition, and we have recently seen Arrhenius, an example of Arrhenius, when we were looking at the Arrhenius equation in the kinetics chapter. But acids produce an H3O+, which is called the hydronium ion, in water. Another way to write the H3O+ in water is to simply write it as an H+ in water. These two are essentially used interchangeably in an aqueous solution. They aren't exactly the same thing, but they represent the same thing in terms of acids producing them in water. In that same chapter, we learned that bases are substances that produce the hydroxide ion in water. Substances that are soluble, hydroxides, metal hydroxides that are soluble, like NaOH, when you put it in water, it breaks apart to give you the sodium ion and the hydroxide ion, and therefore sodium hydroxide is considered a base. Something like hydrochloric acid, HCl, when you put it in water, it reacts with the water to produce hydronium ions and chloride ions, and we can represent it in this fashion, or we can represent it a little more completely like this, and you can see that both of these reactions are balanced. These two reactions represent essentially the same thing, and they can be used somewhat interchangeably. So HCl is an example of an Arrhenius acid. Sodium hydroxide is an Arrhenius base because they fit the definition of what they produce in water. What we want to look at in this next section is we want to look at a definition of acids and bases that does not depend on us being in an aqueous solution. What we'll find is we usually are in an aqueous solution, but we want to broaden our definition to include substances that may not be in water. And so what we'll look at is we'll look at what's called the Bronsted-Lowry definition. The Bronsted-Lowry definition of acids and bases are defined relative to each other, essentially. In the Bronsted-Lowry definition of an acid is a substance that donates a proton, and a base is a substance that accepts a proton. So we have acids donating protons to bases, bases accepting protons from acids. And in this definition, let's look back at our HCl reaction. What we literally have happening here is we have the HCl giving away its H+ to water. And therefore what's left over is my Cl-. When H+ is given to water, water accepts that H+ and becomes H3O+. So this is actually an example of a Bronsted-Lowry acid and base reacting where my HCl is donating the proton, so this is my Bronsted-Lowry acid. The water is accepting the proton, so this is my Bronsted-Lowry base. We don't normally think of water as being a base, but in this definition, using this definition, water is definitely accepting the proton from HCl, therefore water is considered the Bronsted-Lowry base. What we have now is, as we look at a reaction where we have a Bronsted-Lowry acid, we will have a Bronsted-Lowry base because the acid is going to donate the H+ to something, whatever it's reacting with, and whatever that is will be called the Bronsted-Lowry base. So we have these two in conjunction. So let's look a little bit more at Bronsted-Lowry reactions of acids and bases. Alright, as we look at another example of a Bronsted-Lowry acid-base reaction, let's look at the reaction of ammonia with water. If I put ammonia in water, it reacts to form ammonium ion and the hydroxide ion. In Chem 1, we talked a little bit about the fact that this reaction it really does not go to completion. This is an equilibrium reaction. We do not get 100% products here. Ammonia is a weak electrolyte, meaning that in a solution of water, an aqueous solution of water, it only weakly conducts electricity, because although you do have ions, you only have a few ions. So ammonia is a weak base because it's a weak electrolyte. That's all Chem 1 stuff. But now let's look at it within the context of Bronsted-Lowry acids and bases. back up one step. If we look at it in context of Arrhenius acids and bases, we see that when you put ammonia in water, you get the hydroxide ion. This is an Arrhenius base because it fits the definition we were just talking about. But it's also a Bronsted-Lowry base because what is happening as this reaction proceeds is that water is giving NH3 one of its H pluses. If I add an H plus to NH3, I get NH4 plus. Once water gives away one of its H pluses, it becomes OH minus. So NH3 is accepting the H plus. In this case, water is donating the H plus, and so my water is my Bronsted-Lowry acid in this reaction. I have one acid and one base undergoing this reaction, and they're passing a proton from one to the other. In the top reaction, which we still have up here, I have the Bronsted-Lowry acid and base. In this case, water was acting like the base. In the second reaction, water is acting like the acid. A substance that can act as either an acid or a base is called amphoteric. Another word for that is amphiprotic. The amphi or ampho prefix comes from, like, we use it for amphibians. Amphibians can live on either the land or in the water. Amphoteric or amphiprotic. These are substances that can act as either a Bronsted-Lowry acid or a Bronsted-Lowry base. And which one they act like depends on what you put them with. So here we have example of water acting like a base, accepting the proton from the Bronsted-Lowry acid. In this second reaction, we have water acting like the acid, actually donating the proton to the species that it's reacting with. So in a reaction, you should be able to label the Bronsted-Lowry acid and the Bronsted-Lowry base. In addition, let's focus in on this reaction a little bit more. Let me get the other one out of the way. One of the things that we talked about is the HCl donates an H+, that's why we're labeling him as the acid, and what he becomes once he donates that H+, is the Cl-. These two are related to each other in this reaction. Once H2O accepts the H+, he becomes H3O+. These two are related to each other in this reaction. If we look at this reaction in the reverse direction, if we look at it backwards, because all reactions technically are equilibrium reactions, we see that the Cl-, as it proceeds from the right to the left, is accepting a proton. Who is it that accepts protons? It's the Bronsted-Lowry base. So I would label the Cl-, the Bronsted-Lowry base, in the reverse reaction. The H3O+ is donating its H+ to go back to H2O. It's donating it to the Cl-, so H3O+ in the reverse direction is the Bronsted-Lowry acid. Notice that I have an acid and a base on the right-hand side, just like I have an acid and a base on the left-hand side. And in addition, the two that are related to each other, one is an acid, one is a base. The two that are related to each other, one is an acid, one is a base. These two that are related to each other are called conjugate pairs. HCl and Cl-, the two here joined by the top arrow, they are a conjugate pair. HCl is the conjugate of Cl-, Cl- is the conjugate of HCl. We can also say that HCl is the conjugate acid and Cl- is the conjugate base, because that's how they behave in this reaction. And a conjugate pair are two chemical species that are related to each other. One of them is the acid, the other is the base. And you can always tell which is which because the conjugate acid has the H, the conjugate base is missing the H. So the conjugate acid has an extra H as opposed to the base. If I look at this pair, the other conjugate pair in this reaction, it's H2O and H3O+. This is also a conjugate pair. In this case, they both have hydrogens, but H3O has an extra one, so H3O+. H3O+ is the conjugate acid, H2O is the conjugate base, which is exactly how I labeled them in this reaction. If we come down here to this bottom reaction, we can go through the process of labeling it. NH3, as the reaction proceeds to the right, he is related to NH4+. NH3 is the Bronsted-Lowry base, which means he accepts a proton. As the reaction proceeds, he becomes NH4+. So NH3 and NH4+ are a conjugate pair. NH4+ has the extra H+, so the NH4+ is the conjugate acid, the NH3 is the conjugate base, and indeed, as I look at this reaction going in the reverse direction, NH4+, as he proceeds to NH3, he does so by donating a proton. And who is it that donates the proton? It is the acid. This is my Bronsted-Lowry acid in the reverse direction. The OH- is accepting that H+ from the NH4+ to go and form water. As such, the guy who accepts NH+ is the Bronsted-Lowry base. And so I have H2O and OH- are another conjugate pair. They both have hydrogens, but the H2O has the extra hydrogen. The H2O is the conjugate acid, the OH- is the conjugate base.